It's a great pleasure to have Igor Podlubny here. He's been here for almost all of the program. Summer. He's going to tell us about fractional order differentiation and generalized probabilities.
Okay, so thank you, Andrew, and I also thank Codina for allowing me to attend the program. And okay, basically my main field of research is fractional order modeling. And fractional order operators are frequently used for modeling anomalous diffusion, super diffusion, ultra-slow diffusion, viscoelasticity, hereditary effects, and so forth. And somehow my research took me to what I will be speaking about. First, fractional derivatives. So Newton and Leibniz invented calculus, as we know, but they introduced different notation. Newton was using dots that we see now in textbooks in physics. And Leibniz introduced the symbol. And good notation provides a lot of inspiration, actually. So seeing that n, L'Hopital raised the question if n can be non-integer. And Leibniz replied, as you see, that basically it will lead to something like a paradox, but maybe one day something useful will be developed based on this. I like using pieces of history, so this is one of them. The exact date of that correspondence, that reply of Leibniz to L'Hopital, was September 13, 1695. And so, later, this correspondence, it was handwritten correspondence. It was published in the collection of Leibniz works in 1849, and this is how it looked with the exact quotation. So, one day, useful consequences will be drawn because there are hardly any paradoxes without utility. And later, the historical development led to basically three main definitions, and recently a lot of people come with more and more definitions. I call this zoo of different definitions. It is easy to write something. It is not so easy to create something useful. But among useful definitions are the following. The Riemann-Liouville, the name is wrong. The name is wrong. Riemann's name has nothing to do there. You can go to the Moore library, pick up his collected works and see his student's paper. He was a student. He tried to attack this problem and did not succeed and just left it like that. So his name has nothing to do with that. Basically, who did this version of definition was Alexei Letnikov, Russian. So later, a physicist, Professor Michele Caputo, who is still alive and active, by the way, 90-something, 95 maybe, came with his definition version where he interchanged the order of integration and differentiation, and this allowed the use of classical initial conditions, like the function values, the derivative values, and so forth. But also we had a publication with Richard Meighen and Irina Trumarush, in which we made an archaeological discovery in the history of mathematics, and we actually discovered the unknown contribution of Niels Henrik Abel. And already in 1823, he had the same idea as Caputo did. And he had actually the complete Caputo fractional differentiation in that paper, 1823. And Irina Trumarush, my former PhD student, did also translation of the first ever translations of those Abel's work to English. You can find them in archive. They did not fit in the journal publication. That discovery was appreciated by the Abel Prize stuff, and they included our publication in the list of literature on Abel and his mathematics. I like the company. Yeah. And they also added that unknown work of Abel to Abel's works on the website, so you can enjoy that also. And finally, there is the third version, Grünwald-Letnikov definition. Anton Grünwald from Prague, German Technical University in Prague, and Alexei Letnikov, I already mentioned his name, and they did this kind of definition, which was generalization of finite differences. Okay, those definitions look different, but for good functions, they are equivalent. For functions that are sufficiently smooth and has a lot of zeros with their derivatives in the starting point. So, and frequently, very frequently, this Grünwald-Letnikov definition is used for numerical computations. If you omit the limit, you have an approximation in some sense. So this can be developed further, and if you go to MATLAB Central File Exchange, you can find my toolbox matrix approach to discretization of ordinary differential equations and partial differential equations of arbitrary real order, which is a better name, not fractional order, but arbitrary real order. Long, okay, but a better one. And you can experiment with those fractional order derivatives. Here is just one example before I continue, like derivatives of the function sine of different orders. You see sine goes to cosine for order 1, and in between there are some transitional those fractional order derivatives of order between 0 and 1. And that approximation is not very convenient because you have to compute a lot of function values at the discretization nodes, and as the time interval grows, actually you have more and more points. And so there were different approaches to improve this and to reduce the amount of computations, like Neville Ford and Charles Simpson came with, let me say, a kind of a rubber discretization. So as time increases, the discretization nodes are stretched. And other people like Chris MacDonald with co-authors and also late Professor Wen Chen, they came with ideas like this. The most important points are near the current instant. The far past is not so important. So basically, they started aggregating them in clusters to reduce the amount of computation, like that. And here are some basic approaches. A long time ago, I introduced the short memory principle, which says, okay, I have the memory window, and I do not care about the far past. Diethelm, Fried, and Ford actually introduced those non-equidistant grids. So to the past, the distance between the discretization nodes is larger. At the current time, it is dense. And this is that idea with clusterization also. Okay. So now I'm coming to the next steps. There was another edition of Leibniz collected works in 2004, and it included more information than the 19th century edition. What we see here is Leibniz refers to something at the margin, and at the margin he has actually those repeated derivatives and here repeated integrals, and a wonderful thing is here. The sum is just a differential of negative order. And he uses also the notation here, wonderful notation, derivative of order minus e. So basically he had understanding that integrals and derivatives are the same. And he raised an interesting question here. in the same famous letter, absolutely the same letter, he says, we can express those things by infinite series, but what is it in geometry? So here is the question about geometric interpretation of those operators, basically. There are questions that wait for the answer a long time. Here at Newton Institute, we see, you could see that green board behind the glass here, Andrew Wiles, and this some anniversary of his proof of the Fermat-Last theorem. That resisted for 358 years. The Leibniz geometry question had to wait for 305 years until I provided something for that. And there was also another thing. We use a lot of Stieltjes integration everywhere. And Stieltjes integral had to wait for the geometric interpretation for 94 years. Okay, everybody knows about Fermat-Last theorem. Probably nobody knows about Leibniz geometry question, so that was probably the reason for the long time. And this is what I did in 2000 when I was here on the invitation of late Professor David Crichton, that time the head of Department of Applied Mathematics and Theoretical Physics here, and the Master of Jesus College. And this is what I did, the geometric interpretation like shadows on the wall. Basically, I'm using here the Stieltjes integral form of the fractional order integration. And what you see here are like the red shadow is the classical integral, first order integral of the function f. This blue one is actually, this blue projection of this green fence is exactly fractional order integral. Okay, so people liked it and started looking at those operators with great attention. And here is a very interesting development. Very soon, Professor José Antonio Tenreiro Machado from Portugal came with something that he called a probabilistic interpretation of the fractional order differentiation and published an article. And actually, everything was wrong in that article. That was a wrong article. But he had a wonderful observation. He had an observation that the coefficients in the Grunwald-Letnikov approximation of fractional derivatives have an interesting properties. The sum of those coefficients is equal to -1. So if you take them with the negative sign, then the sum of them is equal to 1. And from here, he actually started playing with probabilistic interpretation. That's all. That was the great idea. And Professor Francesco Mainardi, now retired, but University of Bologna, famous also, a student of Professor Caputo, he once sent me an email on some occasion, recalling Wolfgang Pauli, and I like this. This paper would be or must be rejected. It is not even wrong. You know, there is a lot of strange papers published now, exactly of this kind. Nothing wrong, nothing useful. No ideas at all. But Professor Machado's paper was interesting. And that time, I had a conversation with him. And I asked him, do you realize that those probabilities can be negative if the order goes actually above 1? This is the problem. Those binomial coefficients change the sign. And he quoted Leibniz. He had a great sense of humor, and he quoted Leibniz. It will lead to a paradox, and one day useful consequences will be drawn. Okay? It took about 20 years until they were drawn. Okay, now about Monte Carlo. So here we could hear the Monte Carlo term a lot of time, many times. This is the classical textbook example of the evaluation of the integral. So basically, we do uniform sampling and average those values, and this is nothing but the application of the mean value theorem here. Okay. Can you recall Monte Carlo differentiation from the textbook? This is so easy. This is so trivial. Can you recall differentiation, direct differentiation by Monte Carlo method? No. No. Monte Carlo is used in many areas because this is the principle, but there is no differentiation. And if we have integration, it asks for the counterpart. Okay. Until now it was not. And only recently with Nikolai Leonenko, we did the first step to Monte Carlo differentiation. And we did this for arbitrary real orders. And as a particular case, we always have those even integer order derivatives. So the idea is based on that observation by José Tenreiro Machado. And basically what we have is we just introduce a discrete random variable which takes those values k with probabilities equal to those coefficients in Grunwald-Denticke formula, and define the stochastic process. And basically this is what we have. What we have here is f appears outside because we use here the values from 1, and k equals 0 corresponds to pure f. So that's all. And then we introduce those independent copies of that variable, and by the strong law of large numbers with probability 1 for fixed t and fixed h, we have convergence to discrete fractional order differentiation. So the algorithm then is really trivial. So we evaluate the probabilities by using those known coefficients in the Grunwald-Denticke formula. We create that cumulative mass function, throw uniformly distributed random points on that, and okay, that's the rest. Repeating this k times and averaging, we have the output. What is interesting here is the following. The points that we get in this process, these are the points at which we evaluate the function values. And here are different orders, 0.3, 5, 7, and different orders. And you see here that the distribution of the points that we need for our computations changes. As the order approaches to 1, we actually have everything concentrated at the current point and nothing far away, because we are approaching the derivative of order 1. And that derivative is very local. It does not require the whole past. Okay, so this is what we can see. And now we understand, in this sense, why those non-equidistant grids worked. And we also understand that those non-equidistant grids should be created taking into account the order of differentiation. Because here they do not take into account the order. The character is similar, but not adjusted to the order of differentiation, not optimized. Okay, so then we can use this Monte Carlo procedure for differentiation of some examples that we have to produce, and we have produced some benchmark examples. So we need the functions with exact fractional order derivatives that we can compute, and we do those simulations by Monte Carlo, and that's all. So the solid line is the exact fractional order derivative, in this case of the Heaviside function, and the derivative is of order 0.2. And those vertical quasi-lines are actually those dots that appear with repeated trials. Bold dots are those values that we get as averages of those trials. And there are also short horizontal lines which depict the confidence intervals. So, for some other cases, like here, for example, we differentiate the exponential function. For some other cases, the variance is much larger, even still larger. But okay, this is another story because we still obtain the values that are close to the exact values and to the exact values of the function and its derivatives. So this is the Mittag-Leffler function, by the way. It is called the Mittag-Leffler function. It is a generalized exponential. Here we use the Mittag-Leffler function with two parameters, and it also allows that nice exact fractional order differentiation. In some cases, like the sine function, it works very nicely. So this is another topic for research, for which functions we get this or that behavior. So after having this experience with derivatives of order between 0 and 1, we, with Nikolai Leonenko, actually started thinking, what will happen if you go further, above 1? And the problem is there. The problem is there like that. I will tell you the story in a moment. Basically, the problem is that the coefficients in the Grunwald-Letnikov approximation start to have different signs. Okay. Some are positive, some are negative, especially if we go just above 1, then one of the coefficients is negative. What to do? And I did very thorough search, and you know the names. Eugen Wigner, Paul Dirac, Richard Feynman. The common thing is that all are physicists. Yeah? Good. Oh. They have something more in common. They came to using negative probabilities in quantum mechanics. Negative probabilities and negative energies. And here we are at a very interesting point because we all had some education and we were educated that probability is a number between 0 and 1. And I feel that narrow, how to say, perception of that notion for a long time. And to leave this narrow corridor and to go to the left or to the right needs a lot of effort. Those people did this. So Eugen Wigner, he said in his paper, it is here, on the quantum correction for thermodynamic equilibrium, it is 1932, and he speaks that actually it may take negative values, but of course this must not hinder the use of it in calculations as an auxiliary function, which obeys many relations we would expect from such a probability. Okay, so we can manipulate and go further. Okay. The next name I showed you was Paul Dirac, and here is an interesting fact. He was married to Margit Wigner, who was a sister of Eugen Wigner. And maybe they had discussions in the kitchen, I don't know. But actually, in his Bakerian lecture, given in 1941 and published in 1942, he wrote the following: negative energies and probabilities should not be considered as nonsense. They are well-defined concepts mathematically as a negative sum of money. Okay, and so forth. The negative energies and probabilities should be considered simply as things which do not appear in experimental results, but we can use them in auxiliary computations, as Wigner said. And now Feynman came to this much later, and probably he knew about the previous attempts, and he wrote a chapter for this volume in honor of David Bohm, chapter 13, negative probability. And another nice remarks. Yeah? Negative probabilities negative probabilities leads to simultaneously allowing probabilities greater than 1. Clear, because the sum of those must be equal to 1. Okay, but probability greater than unity presents no problem different from that of negative probabilities because they are used as in intermediate calculations and the final result is always expressed in positive numbers between 0 and 1. Okay. And Dirac was actually a Lucasian professor at the University of Cambridge here. And Maurice Bartlett, a famous statistician, definitely was present at his Bakerian lecture, and this is the result. 3 pages only under the title Negative Probabilities. And he says, okay, Dirac was using this, so it's time to get to some mathematical justification of that apparatus. And this is the direct reference to Dirac, to the publication dated 42. And also he wrote, negative probabilities must be always used with, in combination with positive ones to give an ordinary probability before a physical interpretation is admissible. Again, auxiliary intermediate calculations are allowed. Okay. So, Bartlett was inspired directly by Dirac and published in 1945. We know another story, Dirac's delta function, introduced in 1930. Those beautiful relations were just, well, unjustified. And then in 1945, Laurent Schwartz publishes a paper which starts with very emotional introduction. This is really very emotional. He says abuse of the language, and this is not the function, and it needs mathematical justification. Take a look here. Exclamation, exclamation. Read it. And he actually says here, since the introduction of symbolic calculation, physicists have commonly used certain concepts or formulas whose success was indisputable, even though they were not mathematically justified. This is the first sentence. And then he comes to the Dirac. Dirac and also mentions here Heaviside function. Wonderful introduction. If somebody says that mathematicians are dry people, show them Laurent Schwartz's paper, yeah, with those exclamations. So, so those 3 great people also have something common. They all got the Nobel Prize. And first Dirac, 1933, then Wigner, 63, and Feynman, 65. After Dirac got the Nobel Prize, he bought a house here in Cambridge. I managed to find that house. This is the picture. People living there don't have any idea what is the house. There is no any memorial plate. Okay, and also this is the bust of Dirac that you can find here near the reception. So, OM here means order of merit, and this is a very interesting order because it allows only 24 living members at any instant. So, okay. So Dirac was also a member of that order. So negative probabilities to which we came sounded very strange to me. But I already had experience with strange things, like negative norms. Again, everybody knows that the norm must be positive. I already worked with negative norms when I was working with some kind of orthogonal polynomials, which are orthogonal with non-integrable weight function. And there I was using Adamar's finite part integrals that he introduced in 1923. Again, you can go to the Moore library and find collection of his works and find his paper on the initial value problems for linear partial differential equations. It is there. So I knew that norms of positive functions can be negative or even zero. With my colleagues, we had applications of fractional order modeling and in control. So we have working electrical circuits of fractional orders that we use as filters and controllers. And we designed them using expansions in continued fractions. And the coefficients in those expansions dictate the values of the elements in the circuit. And we also had negative values. So what is negative resistance? What is minus 10 ohm? What is negative capacitance? Okay. We found that it is possible to implement using operational amplifiers. So basically a small circuit can behave like negative resistance, negative capacitance, negative whatever. So if you connect this in series with something, you have minus 10 ohms plus 20 ohms, and the total resistance is 10. So we had also this experience, physical experience. Recently there was a paper published and republished in some other journals also, because it is very interesting, on negative capacitance electronics. So basically negative capacitance comes to our real life. And so knowing all that, and taking into account also the existence of signed measures, and probability is a measure, we have an answer. Okay, so why not to consider negative probabilities in this sense? And what happens is the following. What happens is the following. These are the coefficients in the Grunwald-Letnikov approximation, and for different alphas, this is how they behave. If alpha is between 0 and 1, they all are negative. And this is what Tenreiro Machado noticed. The sum of them gives 1, all are negative. Okay. If we go above 1, we have a problem because one of them is negative and the rest are positive. And the sum is still equal 1. Between 2 and 3, we have negative, positive, and the rest are negative. So, okay, 1 is having the other sign. And so forth. Between 3 and 4, we have a more complex thing. We have minus, plus, minus, and the rest are positive. And so forth. So what to do with that? What to do with that? So basically, we separate them, we split them like hot and cold water in the bathrooms here, separate. I also keep the order. Have you noticed that hot is on the left? Good. So what we do is we separate them. We separate them and create two probability distributions. One of them has a countable support. The other one has finite support. The other one has infinitely many values. So with that idea, we take the Grunwald-Letnikov approximation and split it into several parts. One of the parts is, after all, this one, the function and something that is related to the finite number of those different signs. And the rest are those expectations of random variables with that corresponds to positive and negative probabilities. So y plus is a discrete random variable with support I plus, and probability mass function pk, and the y minus is clearly corresponding to I minus and q's. And we do the same. We introduce those copies, repeat everything, average, and after all we have the following result, that those trials converge to Grunwald-Debnikov approximation of fractional differentiation. And those W plus are actually the sums of positive probabilities. These are the sums for negative probabilities. And those terms in front are related just to the function and some finite numbers of deviating terms. So how it looks in particular cases? It looks like this. If alpha is between 0 and 1, then we have the following Monte Carlo basically scheme here. And the support for this y minus, because those probabilities are all negative, you see, is 1, 2, 3, and so forth. The coefficients are the same binomial coefficients. If we go above 1, alpha is between 1 and 2, then we have one of those terms with that I mentioned already appearing in front of those sums. And what we have here is actually we like extract the first term, and then the support is actually focused on 2, 3, and so forth. So one of those things we extracted here. So this one corresponds to this W1 corresponds to this minus alpha f t minus h, and so forth. The rest is here. Between 2 and 3, we have more terms outside, like again here, 2 and 3. And so here we have the same, only one value is here, but what happens is that the support is here, 1, 3, 4. So 2 is dropped. 2 is dropped because it is here. And 2 contributes to this term for orders between 2 and 3. Finally, as an example, the case of alpha between 3 and 4. And here we have both present, y plus and y minus. And 1 plus has that infinite number of values. 1 is dropped and 3 is dropped, so 2, 4, 5, 6, and so forth. And y minus has only 2 values, 1 and 3, that are dropped from here with the appropriate probabilities. And so basically what we have here is another scheme for the Monte Carlo simulation for orders between 3 and 4. Some examples here also. For example, alpha is equal to 1.7, and here is the pair of the function in its derivative of order alpha. The function sine is a particular case of the Mittag-Leffler function. And for the Mittag-Leffler function, we have a very convenient rule for the differentiation. And when we apply that rule, we have this. I told you that the Mittag-Leffler function is a generalized exponential. So it is easy to differentiate or integrate exponential. for the Metag-Lefler function, it is also not so difficult. We just subtract the order of differentiation at two places. Some power law term in front and the second index of the Metag-Lefler function. So this is one of those cases. If alpha is, for example, 2.7, this is also another case. Lambda here is 1.2. And even this strange behavior is captured with minus infinity here and some oscillations, undamped oscillations actually, for growing t. We have a toolbox for this work, which is still ongoing, Monte Carlo fractional differentiation toolbox. So there are examples for our papers with Nikolai Leonenko, and the papers were published in 22 and in Fractional Calculus and Applied Analysis journal. And basically, with my colleagues, we always do this. We publish a paper and a toolbox. So everything is verifiable and reproducible. So basically, what you see in our papers, you can reproduce. And then you have more confidence in using those tools for your own problems. And so okay, so speaking about those negative probabilities or signed probabilities precisely, I can tell you that searching for information and tools for simulation actually produced an interesting result. There are theoretical works on this, like signed probabilities, but there are no tools for simulation. Even in this case, which is relatively simple, when we have only a finite number of terms with different sign. Okay, those results that I demonstrated can be improved using standard tools like reduction of variance, importance sampling, stratified sampling, and so forth. We got, with this tool, better understanding of non-equidistant grids, so why they work and how they can be better designed. Then we also obtained a very convenient way to parallel computations, because Monte Carlo method is very suitable for parallel computation. So this is what we got, a very interesting perspective. And we are going to use this approach for solving differential equations with fractional order derivatives also. And definitely there is high potential for applications. We still continue with our work. Also, I recall another quotation provided by Professor Francesco Mainardi, and he recalls great Italian Francesco Tricomi, and he says, even if I may not have always succeeded in simplifying difficult things, I hope that no one will ever find me guilty of artificially complicating easy things. I also like this. And I also want to show you this photo. And this photo is related to our ongoing work. And it was taken on the first successful numerical simulation of signed probability distribution with infinite number of positive and negative terms. And if the situation is like this, the previous derivations that I showed you, they do not work. those derivations work when the number of sign alternations is finite. And they do not work for infinite alternations of signs. And in that case, other tools should be used, and we succeeded for the first time on September 13th. Room M13, right near Andrew's room. So, thank you very much for your attention and your patience. And I would like to thank the organizers again, and also the Newton Institute for providing this opportunity to stay here, to work here. And I can also say that I learned a lot during this program, although it was really more stochastic than deterministic. And as you could understand from my presentation, I came from the deterministic side, unexpectedly, to this stuff. So, thank you again.